creepy screen, YouTube channel up and ready. So I've been working on some class stuff that I wanted to show you. First off, the online homework system is ready to roll. So this is your chance to earn 3 points of extra credit. Think of it as a free late assignment by making sure that everyone knows how to use this and that all of your logins are working correctly. So if you'd like to follow along with me, we'll do a quick demo here in class. The CLDP 945 homework portal link is alive. You should be able to sign in with your last name and your KU ID. I'm going to use one of my many dummy logins. You should see a page that looks like this. You all have it? Hooray! Everybody's login is working. So homework 1 is already available. Homework 0 is the thing I'd like you to do by Friday for 3 points of extra credit. Note that we also have here zeros where throughout the semester, periodically updated will be your various point totals. So homeworks, quizzes, bonus points, and your current grade. So you'll always be able to figure this out. Every time a homework closes, it doesn't update immediately. I have to go through and look at the homework and do a few keystrokes just to make sure that everything is okay before it updates. So I have that level of quality control built in, but it should be updated reasonably soon after each homework is due. If you click on homework 0, this is my traditional free credit, 3 credit, free credit assignment to do over the syllabus. So this demonstrates the types of homeworks that you will get this semester. If there are any individual specific data files to be downloaded, they will be right here. You'll have instructions followed by 2 different kinds of questions. So computational questions are shown in the first set here. So just as an example, how many regular homeworks are currently planned? 8. So if I put in something besides 8, let's say I put in 9 and I hit enter, it turns red. That means you do not yet have the right answer. If I turn 8, it turns green. How many points are those homeworks worth this semester? 88. Yes, someone's reading the syllabus. How many points do you lose if they're even 1 minute late? 3. And why do I do that to you? Is it because I'm mean and vindictive and punitive? No. Any ideas? Yes, motivation to stay with the class because things with real deadlines get done, right? Conference proposals, final exams, things with real deadlines get done, and I know this, so I want you to think of it as real. However, I will remind you that I also know that you guys are real, meaning that this is not your only thing in your lives. So anytime you look at the schedule and you think, oh, that week is going to be bad, I'm going to be out of town, I'm doing comps, I'm doing this, I'm doing that, let me know at least 2 weeks in advance and I will give you an extended due date. If you are planful about it, I'm happy to work with you. Otherwise, the due dates are real because I really want you to keep up. That's my motivation. So yes, 3. How many points of extra credit do you get for doing this with me here? 3. So you get 1 free late homework, just right off the bat. The other type of questions that you will see are either going to be this type, which I call Mad Libs, fill in the blank, or they will be multiple choice questions. So your instructor this semester is me. My office is which one? Yes, 3042, although my office hours will be held in this one, yes. 6,000 Dole does not seem likely. That would be up on the roof. And my office hours will be held, oh, with the typo. Mondays and Thursdays. It should be Mondays and Wednesdays. My bad. How many points from participating in out-of-class quizzes? 12. How many days a week does this class meet? 2. And yes, I don't really take attendance. I do expect that you'll show up most of the time if you can. If you know you're going to be gone, you can let me know. If you need to miss and you don't know that in advance, that's okay too. I expect that you're all graduate students and you can all manage your own schedules and lives and that I don't have to be your babysitter, right? We're all good, right? This is why I love grad students instead of undergrads or high school students or junior high or anyone else. So you'll note that every time I submit something, there's a box here where you can hit check and save, or you can hit the enter key. The computational ones turn green, but nothing happens to these ones. So these fill-in-the-blank questions and the multiple choice questions only turn red and green after the due date. So you don't get a chance to fix those, although you will get a chance to see what the right answer was if you get the wrong answer. This class will utilize SAS, which is currently available for purchase. Which one? Once or once a year? Once a year. Do I want you to spend $150 a year on this? No. Where else can you get SAS? All of the above, yes. And if you haven't done so already, please try out Remote Desktop as a backup in case you need to get access to SAS outside of class. All of you should have logins that allow you to log into each of these computers using the IP address. So if you have any problems with that, let me know. So after you've finished the computational questions, it will let you know that they're all done. When you want to submit, there's a submit button here, submit final answers, but you're not done yet. Just in case you hit that button accidentally, I'm asking you to then put in your KUID again to make sure that you know that you're submitting. So all of these answers here that are not yet graded are black, showing that they are not yet ready. So I'll go 1, 2, 3, 4, 5, 6, 7, and there. Then after the due date passes, you should be able to log back in and see what you got. So most of you have done this before, but a few of you are new. Any questions on that process? Okay. To remind you my strategy for homeworks, obey the 15-minute rule. If you have tried entering the same box for 15 minutes in a row and it hasn't turned green yet, stop. Stop and ask for help. Send me your code, send me what you think it should be and why you think it should be that, and I can check it against the database and see how far off you are or otherwise help you troubleshoot. They do pay me for that, so you should feel allowed to take advantage of that service. Deal? Deal. All right. Quiz 1 is out-of-class quiz is due by 1 o'clock on Wednesday. It is available on Blackboard. These quizzes are participation-based. If you write down something and give it a real effort, I will give you your 2 points. The right answers we will go over in class, and they will also be available after the due date passes for each of these quizzes. If you are late in doing a quiz, you can still do it, but then you get 1 point off, so you get 1 point instead of 2. So those will happen every other week, essentially. On the off weeks, you'll have a homework assignment due instead. That's my idea. We'll try and keep the schedule so that it doesn't get too overwhelming at any one point in time. All right. Wow, I am warm. Okay, I'm gonna have to start wearing shorts to class again, even though it's like snowing outside. Any questions? All right, are you ready to do a little more reviewing and then have some story time? Why not, right? That's why we're here. So let's pick up where we left off. Roughly, let's see, I started looking ahead here. We were doing a lecture 1 review. Should we review the review? Would that be useful? Maybe? Okay, so we are talking about terminology, levels of analysis, what the class is going to be about. The class is about multi-level models broadly construed, modeling dependency. What does dependency mean? Correlation, there you go. That means that observations from the same something are likely to be more alike than observations from a different something. Right now we have time within person, but we'll generalize that to other kinds. Time is where we're starting. We are looking at types of longitudinal data with additional types of complexity. We'll talk briefly about ANOVA across the course of the semester as an alternative to these. We looked at modeling variance into 2 piles. So let's do one of my Excel type reviews on vocabulary. That way everybody can see it a little better than writing on the board. So in multi-level modeling terms, level 1, level 2. Let's see here. I'm going to make a thing called inference here. And by that I mean between or within. Which goes with which? What's level 2? Between. In the context of longitudinal data, it's between persons and within persons. In other kinds of samples, such as people in groups, it might be between groups and within groups. But the words between and within will always hold as level 1 and level 2. I'm going to say type of variance. I'm looking for terminology here. Both types of variance start with an R, so that doesn't help. Random. Which one's random? Level 2. If I had a level 3 in here, would it be random also? Yes. So anything above 1, random effects. What's the word that I use for level 1 kinds of variance? Residual, yes. Letters that go along with these. We'll go variance letters. What is the symbol that shows up in your equations for random effects? U. What's the symbol that shows up in your equations for level 1 effects? E. So always notation is author specific, but once you get used to seeing these in a particular format, even if someone else uses different letters, you'll be able to see what's what. So the level 2 has one kind of variance term, it's always going to be some kind of random effect. Level 1 has some kind of variance term, it's going to be some kind of residual or error. Matrices in SAS and a lot of other places. Where do the U random effects variances and covariances live? I'll give you this as multiple choice. V, G, R, or Z. G, level 2 random effects variances and covariances live someplace called the G matrix. Level 1 variances and covariances live R, very good. Just R, thanks. When you put them back together and you get V, yes. I'm reticent to do my usual cheerleader move because I'm probably pitting out my shirt, but I'll do it anyway. V! My goodness, it's hot in here. So what is that Z thing then that I put in my list? I don't normally talk about that. Z is what SAS calls the variables, the predictors that have random effects. So it's a matrix that holds the values of the predictors that have random effects. It wraps around the G matrix to make it the right shape to be added to R to be able to become V. It wraps around the G matrix to be added to R to become V. So yes. So conceptually, what Z does is it holds individual specific information, which occasions they have, how many they have. It's what allows each person to have their very own custom V matrix and why MLM can handle incomplete or unbalanced data. It's because of this custom V, and Z is what makes the custom V. Speaking of handling data, how does multi-level modeling handle missing data? It doesn't. What does it do? It does list-wise deletion of what unit? Occasions, or level 1 units. That's the catch. Incomplete rows still get deleted from your analysis, but what a row is no longer a person. It's an occasion within a person. So you do get to keep whatever data from a person you do have. Let's see, what am I missing here in my thing? Oh, words. There. So if I'm talking to somebody who's not like, oh, G matrix, yeah. What are the words that I put in here? What kind of differences or variation are we talking about here? Those are the words, inter and intra, which is which? Intra, inter. Intra is which one? Intra, intra, inter. Inter, and then depending on the context of the study, inter-individual, interpersonal, inter-school, right? In the same way that between works for everything, inter works for everything. What goes after that? You can put in variance, variation, differences, whatever, right? Those are more or less synonymous. Okay, I think that's all of them. Can you think of any I forgot? Okay, cool. We got it then. Let's see, what else do I want to review? We got the words, got the models, intra-class correlation. If I have an ICC equal to 0, that means all of my variance is which kind? Level 1. If I have an ICC equal, what's the highest it can be? 1. Now where's all my variance? Level 2. Which of these is bad news for somebody who's going to be the first in their field to do a longitudinal analysis? ICC equals 1 means game over. It means all of your variation is between. All of your variation is in mean differences only. And there is no longitudinal to be had. Related question. What if I have an ICC between 0 and 1, and I put in a fixed effective time, and I find that it's not significant? Does that mean that I don't have longitudinal data? No. It means I don't have linear change in the means over time. But so long as I have an ICC less than 1, I do have longitudinal data. It's just of some other functional form, or perhaps it's just fluctuation. So this idea of what kind of time is relevant shows up this picture. This is what I'm going for. Both of these pictures show an intra-class correlation somewhere between 0 and 1. The picture on the left would be more likely to have a significant fixed effective time as well as a significant random effective time than the picture on the right. The picture on the right is still longitudinal though. It's fluctuation rather than systematic change in any one direction. Okay, let's see, what else do I want to do? I want fixed and random. This picture. Who wants to tell me why C is labeled the way it is? That's the trickiest one. Sir.
The fixed slope is not significant, but there are random differences between equal groups.
So what does it mean that the fixed slope is not significant?
Overall change over time is not significant. Flat.
Yes, on average, the means do not change over time. However, what the rest of what you said?
However, the individuals do change over time.
Yes, there is individual differences in change. People need their own slope. In each of these pictures, people need their own intercept also. In the top two pictures, the common denominator here is no random slope, meaning the intercept differences that were there at the beginning carry through, parallel lines. So it doesn't really matter where the intercept is because the variation around it would be the same at any occasion. In the bottom two pictures, C and D, it matters where the intercept is. For instance, if I had the intercept at the beginning here in picture C, I may have a very small intercept variance because it's conditional to wherever time 0 is. If I put time 0 out here, the intercept variance would be much larger. So variance changing over time is a hallmark of random effects of time. All right, we did that. We did equations. We did that one. All right. Do you want to go over equations? We're going to do that a lot in the stories too. Let's do like this slide, slide 26. So this is stepping up one at a time from the simplest possible model for two-level data. What makes the first model here two-level is that it has two different variance components that are uncorrelated. So I have a between-person variance in the intercept, U0. I have a within-person variance in the residual, ETI. That's what those letters indicate. What I'm actually estimating is not what the U is for each person or what the E is for each person in each occasion, but their variance across people, as well as this thing, which is my fixed intercept. So in this model, the fixed intercept is just the mean over time. Once I add some kind of effective time, then the intercept becomes conditional on when time is 0, which is what you define based on how you specify time in the model. I'm calling this fixed linear time because the equation for beta 1 here at level 2 has only a fixed effect. So that means everybody gets the same slope according to this model. Whether or not that slope needs to be linear, whether or not that slope should be the same across people, those are empirical questions. So this is a simpler model against which we can compare more complex models. And then last but not least, we add the random slope. The U1 gets picked up here, and yet another typo that I swear I've fixed and it comes back. That's a 1 right there, folks. There. As well as the covariance between the two. All right, and I think, yeah, this is about where we got, this is where we were. So any questions on what we've reviewed so far? Okay, next step, more somewhat arbitrary topics, and then we'll get into the stories. Significance and effect size. So more and more often, journals are requiring explicitly some kind of measure of effect size for everything. Effect size in multi-level models is a little trickier. You have to decide which kind you're going to report and how you want to calculate it. So I'm giving you a few of these here to start with. Talk about significance and effect size on both sides of the model. So we'll pick up on slide 28 here. So model for the means, fixed effects, what happens on average? You do not need to do any kind of log likelihood model comparison, anything for this. You could, but you don't need to. This is the stare at the p-value option that you know and love from regression and every other model that you've ever seen before me, right? Stare at the p-value, it is there. I see Amy's like, heck yes, stare at the p-value. Now the only catch to this that I've introduced in terms of complexity is that your p-value can be univariate or multivariate. So univariate meaning like I have a slope, is it significant? Multivariate being something like, do I have a main effective group where I have 4 groups? Then that's a 3 degree of freedom question. Do I have an effective group? That's a multivariate wall test. But you still get an F or a chi-square on your output that tells you the answer to that question. You would then delve more deeply into that 3 degree of freedom test to figure out which groups are different from which other groups. So whenever we're talking about fixed effects, you will not see me referencing log likelihood. Most of the time, we don't need to. We can get the answer directly on our output using univariate and multivariate wall tests. By the way, just as a technical aside, I once got yelled at by somebody for using the term wall test to refer to F's and T's that have denominator degrees of freedom. Technically speaking, a wall test is for a Z, but if you have a T instead of a Z in which you have degrees of freedom, I would just call it like modified and then say what kind of degrees of freedom you use. To me, that's a 6 of one, half a dozen of the other. But degrees of freedom are more relevant in smaller samples than larger samples. Now, model for the variance. This is where we need to do some kind of model comparison to decide what we keep and what we drop. So what is the pattern of variance and covariance? How many random effects do we need? Are our residuals still correlated after accounting for random effects? All those kinds of questions are phrased as model comparisons. We do need the log likelihood or the -2 log likelihood to answer that. We cannot stare at the p-values that show up on the output from the Wald test. Those are based on the idea of a two-sided sampling distribution. So if I have a fixed effect, could a fixed effect be positive? Sure. Could a fixed effect be negative? Could I have a negative slope? Sure. Can I have a positive variance? Sure. Can I have a negative variance? Some people would argue that you should let them go negative, but I am not one of those people. No, you can't have negative variance. The smallest kind of variance you can get is a constant, right? That's like the definition. So because variance can't go negative, its sampling distribution can't be approximated by a regular two-sided one that the Wald test uses. So that's why you can't stare at the p-values. It gets more wrong the closer to 0 your estimate is when you actually need it. So what do you do instead? We'll talk about that. So just to remind you, all of these terms here, any fixed effect, what does the Wald test consist of? An estimate, a standard error. That estimate divided by a standard error is then given as a t-value or a z. And I'm saying this because you'll see it labeled differently across different programs, but it's the same information. Whether or not you're treating it as a t or a z depends on whether or not you're using denominator degrees of freedom of some kind. Programs like Stata and M+ do not. Stata added denominator degrees of freedom in version 14. Programs like SPSS and SAS do by default. So it's just program-specific differences in what they do for these kinds of models. But you get a p-value that goes with this t or a z, excuse me, and you get some kind of confidence interval around the fixed effect. So this confidence interval that shows up on your output describes the certainty around that estimate itself. Like how certain that we get a slope of 2 if we redid this study 100 times. Like it's about the estimate itself. That's contrasted with another kind of confidence interval that we'll talk about in just a minute. Here's just a quick reference table as to what letters you get and what to call them. So if you have a univariate Wald test in software that's spitting out degrees of freedom for the denominator, that's going to be a T for a single test, an F for a multiple test. If you're in software that isn't using denominator degrees of freedom, such as M+, then you get a Z per test, and if you get multiple tests at once, that's a chi-square. F, let me try to remember how it goes. F times degrees of freedom in the numerator is chi-square. So you only need one or the other. You can ask for either or both in most programs. F times degrees of freedom equals chi-square. Numerator degrees of freedom. I might be saying that backwards, but I think that's right. So point being, you need one or the other. What you get just varies as a function of what program you're using. So this is significance. For fixed effects, this is pretty straightforward. Effect size. I've given you two different kinds of variance accounted for measures. They are complementary. You might use both. You might use one or only the other. The first one here, which I think is unique to multi-level models, and so I want to spend more time making sure you understand how to get it, Pseudo R Square. This is the universally agreed upon term. This is not me being funny. That's really what it's called, Pseudo R Square. It's the idea of variance explained per pile, per variance component. So for instance, if I back up a minute here and I go to these models again, if I'm in this first model right here and I start plugging in predictors and looking at their fixed effects, how many possible R-square values would I have if I'm using Pseudo R Square? How many kinds of variance could I compute a Pseudo R Square each for? How many blue things are there? 4 blue things, but how many blue estimated things? 2. I have U0 variance. That's my level, please don't get it wrong. 2, yes, that's my level 2 random intercept between person intervariance that lives in the G matrix. I've got that one. And I have my level 1 E variance that lives in the R matrix that's intra, that's within. I've got that one. So I've got 2 levels, 2 kinds of variances, 2 potential pseudo R squares. How much of the between variance did I predict? How much of the within variance did I predict? Let's look at this next model here. Have I added any fixed effects? How many? 1. What's it for? Linear time. Is linear time a level 1 variable or a level 2 variable? You kind of can't tell from the equation, right? Because it shows up in both. But where does the time variable show up? Level 1. Said differently, is time a time variable or a people variable? A time variable. So if time is level 1, and in this case I'm assuming it's purely level 1, that's our next topic after review, then which of my 2 variances should it have reduced? Not a trick, I swear. Residual, level 1, the one that's in its equation. This effective time right here should have reduced this residual variance. Now what happens if we move to this model? Have I added any more fixed effects in the bottom model? No. What did I do instead? I added a random effect. Should I be talking about pseudo R square? Let me phrase that more obviously. Should I be talking about pseudo R square? No, because I made a 3rd pile. That's what I did. I can't talk about variance reduction in a 2-pile model versus a 3-pile model. They're allocated differently. So I haven't explained any variance. I have reallocated variance from what I thought was level 1 residual into what is now individual differences in the linear effective time. I'll say that again. I have reallocated variance from what I thought was level 1 residual into what is now level 2 individual differences in the linear effective time. Now to see how that might play out, let me go back to the previous slide here. The E's are the level 1 residuals. It's how far off your line are you today? What would happen to those E's if the slope of that blue line was made to be the same as the slope for the black one for the overall sample? E's get bigger. The deviation would be bigger because it's the wrong line. So what we thought was just time-specific variation was actually systematic, was specific to the individual. Part of the reason why this person's E's would have been wrong is because they needed their own line that was steeper than everyone else's. So part of what we thought was E at level 1 actually becomes another kind of between-person difference. Between-person differences in linear change. So at this point, if I were to add predictors, how many kinds of pseudo R squares would I need to calculate? Well, I had 2 before, right? So now how many do I have? If I added a random slope? 3. 3 kinds of variance in the last model here. E, level 1, why are you off your line? Level 2 U0 intercept, why did everybody start out differently? Level 2 slope, why did everybody change differently? So that's why you can't just say like the R square for the model was 0.3. It's like, what model? Which one are you talking about? If you're using pseudo R square, you have to call it that. You should probably provide a reference. My book would be nice if you'd like. I get like $2 every time I sell a copy still. No, I'm actually not kidding. It's not that much more than that. But yes, helpful to provide a reference. Any multi-level modeling textbook would do. It would be nice if you gave mine a shout out, since I'm here sweating my butt off in front of you. And you have to define it. We calculated the proportion reduction in each variance component, comma, i.e. pseudo R square citation as, you know, and then give the formula. Jacinta.
Yeah, so if you're reading an article and they are talking about just R squared, they're going to be using the first model?
I don't know what they're doing, to be honest, because it's either pseudo R square or the one that I'm going to compare it to is total R square. If they just say R square, that's ambiguous.
Okay, and that doesn't necessarily mean it's a univariate model, it just means
The only instance in which a single R square is okay and doesn't need to be questioned is if you have a single level model with one variance component. Then that's all it could be. But anytime you introduce more than one kind of variance, you introduce more than one kind of R square. And so even if someone calls it like, you know, the ZWQ R square, and you're like, what the heck is that? Like if they give you the formula, you can be like, oh, they just renamed it into something else, but I know what this is. So give the name, give the reference, give the formula, and then people will be able to follow what it is. And so then when you're talking about variance explained, you have to qualify it. I have, you know, 30% of the variance explained in the random intercept. I have 15% of the variance explained in the random slope. I have 0 variance explained in the residual, for instance. So each pseudo R square value, then you're referring to a particular variance component. Yes, go back to that.
After I only add time invariant predictors, I will talk about the change in.
We'll get to that. Which one goes down depends on what type of variable you've added. So it's not that simple, unfortunately. So let me go back to slide 21 and talk about pseudo R square for these models here. Other questions? No? No? So if you add time, and time is a level 1 variable, it should make the residual variance go down. If it makes the residual variance go down, it will also make the random intercept variance go up. So pseudo R square for the random intercept will be negative. It's a consequence of how these two things are calculated together, estimated together. So just to remind you that this will happen, the random intercept that you get on your output is not just the between variance. It's the between variance that's been corrected for how much of it SAS thinks is due to chance, is due to level 1 fluctuation. How much it thinks is due to chance is captured by the the residual variance divided by the level 1 sample size. So if you just look through the numbers here, if what I really have is between person intercept variance that's 4.65 and my residual variance was initially 7.06, what's going to show up in an empty model as all the between intercept variance there is 2.88. If I then explain, these numbers are from chapter 5 in the book, if I then explain about 70% of the residual, I drop that level 1 residual variance from 7 down to 2. The correction factor is also reduced, and so it makes it look like now there's more intercept variance than there was before. Gesundheit. So I say this point to you for 2 reasons. Number 1, there's going to be a point at which you forget about this and you try to calculate pseudo R square and you realize that it went negative and you're like, did I do something wrong? No, you didn't, number 1. And the other reason I point this out is because there may be instances in which you run your empty model and you get an ICC of exactly 0. And so you think, well, I don't have any between variance. I don't have to worry about it. I don't need a multi-level model. I only have one level of variation. But what's going to happen to that ICC of 0 the second you reduce the residual variance? It's going to go up past 0. It's going to come back. So an interclass correlation that was initially 0 is not going to stay 0. It can be much, much larger once you add predictors to explain the residual variance. So the answer to, do I need a multi-level model, is probably always yes. Even if initially it looks like no, because it can change. Now that being said, if it's an ICC of 1, do you need a multi-level model? You do need one if you are going to use all the data you collected, because it still has to know that each person has carbon copies of themselves in the data set. Or you could just switch to a single level model and use one occasion in that case. That would be another solution. All right, so that is significance for fixed effects, straightforward. Pseudo R square is one way of measuring variance accounted for. We'll talk about total R square as another. Then we're on to the side for the variance instead. So how do you decide what kind of model for the variance you need? Meaning, how do you decide which effects should be random and which should be fixed? This is where we talk -2 log likelihood comparisons. Like log likelihood, this is literally the sum across persons. So right there, that tells you that any analysis in which you are comparing these log likelihood values has to be the same persons, has to be the same data. Otherwise, the sums are not comparable. It's the sum across persons of how likely their set of observations is given the current instantiation of the model parameters. So it uses this value to try and figure out if you're at the best parameters or if not. And once it decides it's done, that it's at the best, it spits out this number. So an example log likelihood might be something like 4006. Sarah, what do you think? Is 4006 a good answer? Maybe. Does it mean anything? No. It doesn't mean anything until I know that I ran another model and I got 4010. If the log likelihood goes up, it's a better model. But what you get on your output for these models is -2 log likelihood to help you facilitate comparisons between them. Which means -2 log likelihood should go down if it's a better model. So most of the examples we're going to be working with are phrased in -2 log likelihood already. So smaller is better. -2 log likelihood, that quantity is sometimes called deviance. So that can help you remember deviance is bad. You want less of it. We have 2 flavors of likelihood to keep track of, maximum likelihood and restricted or residual maximum likelihood. To compare models, they both must be in the same flavor. Here's a review of how to do a likelihood ratio test. So this same process is called a chi-square test in SEM. It's called a deviance test in MLM. Likelihood ratio test is sort of a generic term that holds across disciplines. I tend to report -2 delta for the big triangle log likelihood. Some people report that as chi-square in their paper. Either one of those is fine. So we calculate the difference in -2 log likelihood, where it is the model with fewer parameters minus the model with more. We calculate the difference in degrees of freedom, which is the number of things we've added or subtracted. And then we compare that difference to a chi-square distribution with the degrees of freedom. You can then get your p-value from chi-square functions such as in Excel. Some programs have a likelihood ratio test. R does that, Stata does that, and so forth. So generally speaking, if you've added parameters and you have a significant -2 log likelihood test, then your model has gotten significantly better. If you've added parameters and the test is not significant, different types of statistics are phrased in different ways. So for instance, in multi-level modeling, most of the time we're adding things. We're deciding if we start with something that has just a fixed effect and we add its random effect, is that better? In contrast, in worlds like structural equation models, you're always trying to see if your model fits. Well, what does that mean? It means you start with the perfect model and you see if yours that's simpler is not worse. So it's the same process, just with a different frame of reference. So I want you to be used to thinking about it in either way. What does it mean if it's significant? Depends on which way you're thinking about the problem. The more complex model fits better, the simpler model fits worse, if it's significant. There's also these things, AIC and BIC, that you can look to as supporting evidence. They have no significance tests, and that's why I tend not to worry about them too much. REML versus EML. Okay, so FIML, is this a word you've heard of? FIML handles missing data, right? No. Full information maximum likelihood is what that stands for. That's what we're doing, folks. In proc mixed, in SAS, and in every other kind of mixed SPSS, data, M+, whatever, it's full information. What that means is when you have continuously distributed data, continuous residual types of models, you're using all the data to build the likelihood functions. You're not summarizing the data first. Do you know what it's called when you summarize the data first and then you run some analyses on that summary? If it's not full, what is it? 948 people, you should know this. It's not empty. You think that's the opposite of full, but not in this case. No. Actually, no, and that's why this terminology is so challenging. So like if I do WLSMV in M+, for instance, what kind of information is that? If it's not full, limited, yeah, that's the contrast. So for instance, if you get somebody's covariance matrix out of an article and you run a path model on it, you can totally do that, right? But that's a limited information analysis because you started with a summary and you're using that. This distinction doesn't matter if you have complete data. The summary is good enough. It matters if you have incomplete data. So everything that we're doing is full information, both regular flavor maximum likelihood and what's called restricted or residual maximum likelihood. They're both full information. The difference is in whether or not they take into account the uncertainty that comes along with simultaneously trying to find the fixed effects. REML does, EML doesn't. REML is better. REML is less biased when it comes to estimating variance components in small samples. It's also less biased in large samples, but the bias is so trivial that no one cares. So why are you only now hearing about residual or maximum likelihood? Because it's only possible for certain types of data. What it does is try to maximize the residuals of the analysis and then find the fixed effects secondarily, as opposed to maximizing the whole data. So REML is only possible for outcomes that have a normal residual distribution. So there is no such thing as REML, for instance, for binary outcomes or count outcomes or any of those other kinds. That's why the world of structural equation modeling doesn't have REML in it, because it usually needs large samples and because REML is only available for continuously residual data. So I make this point because what we're doing is still maximum likelihood, even though it's called restricted maximum likelihood, and that sounds bad, right? It's not. It's actually better. It's residual maximum likelihood. This distinction matters when you're doing your log likelihood types of comparisons. And so I have several slides in here just illustrating these rules here, but here's the big one. If you are in REML, which is where we're going to be most of the time because it provides the most accurate variance components, your models to be compared must have the same fixed effects or it's not valid. That means they can only differ on their variance side, on their random side. Keep the fixed effects the same and you're good. If you're in ML, you can compare any kind of nested model. It can differ in fixed, random, or both. So ML is more general in that regard. But I maintain this is not a problem because we can always test differences in fixed effects directly. We can stare at the p-values that show up on the output to do that. The only types of model comparisons that we need to do log likelihood comparisons for are variance comparisons, and that's exactly what we're talking about here for REML, variance comparisons only. So these are the bigger picture rules. I've set up all of our examples so that you're not in danger of violating them. Whenever I test new random things, I keep the fixed things the same. And that's that stuff. Yeah, that's that. No, you can estimate anything, but you can't compare their -2 log likelihoods. I mean, you can do it, and you'll get a number back, but it won't mean anything. Because it's maximizing the likelihood of the residuals, where the residuals are sort of after the fixed effects have been taken into account. So it doesn't pay attention to how well they did. So if you have different fixed effects from the get-go, the residuals aren't comparable. Totally, totally you can make a mistake, yes. Nothing will stop you. There's a warning that shows up in Stata if you try to do that though, but it will still give you an answer. So do you need to worry about this in M+, for instance? No, M+ doesn't even have REML. So you have to worry about this when you're using a program that has REML. And when should you be using REML? I heard it. When the fixture, well, REML for estimation, not for model comparison. When does it matter? Small samples. Small level 2 samples, small highest unit samples. Less than 50-ish, you need to worry about this. Lucas is like, oh, thank goodness. I have thousands of countries and groups and things. I'm good. Yes, if you have thousands of something, knock yourselves out. ML is just fine. So these are all about significance tests, what I'm talking about. Is a given random effect significant? Does it help the model? How do you talk about effect size for random effects? Given that random effects mean you've added a new pile, it doesn't make sense to do pseudo R square. What you can do, though, are two different things, and they are descriptive. One is random effect confidence intervals. So we looked at these last semester and did several examples of these. So for instance, if I have a fixed slope of 1.7 and I have a variance around it of 0.9, and that number is significant, then I know people need their own slopes, but how do I talk about that? Well, for any term at level 1 that has both a fixed effect and a random effect at a higher level, you can compute this interval. The center of the interval is the fixed effect. A 95% confidence interval is given by 1.96, you can pick whatever value for other confidence you want, times, what's the square root, I'm working on that, what's the square root of a variance, folks? Standard deviation. So this is like, well, here's the middle is the fixed effect, and what's 2 standard deviations on either side? So this is used to convey how variable the effect is across people. So these are two different kinds of confidence intervals that people are talking about, and this is a source of confusion I found for readers and reviewers. One kind of confidence interval that shows up on your output is around the fixed effect. So if I take my fixed slope, for instance, of 1.7, and let's say that it had a standard error of 0.2, then I would go 1.7 plus or minus 0.2 times 0.2 describes the interval around this 1.7, meaning if I replicate this study lots of times, how precisely am I sure that my fixed slope would be 1.7? That confidence interval has to do with whether or not that thing is significant as a slope, different than 0. What I'm talking about is different. I'm talking about how variable are my people slopes as given by the fixed effect and the random variance around it. So in this case, those two numbers, when put together, give me a confidence interval of minus 0.15 to 3.59. So that means on average, there is growth. On average, people improve by 1.72 per unit time. However, not everybody is predicted to improve. The variance around that slope, given by the random slope variance, means that some people go up a lot, and some people are actually predicted to go down or not change at all. So I like this process. This is something I borrowed from the Snyder's and Bosker's multi-level books because I think it puts it into terms people can understand. How variable are the slopes? I know it's significant, but how much is it? It's this many units per x. So we've done those a lot Any questions on those while we're on this? Okay, one more thing I wanted to show you, we touched on at the very end of the semester, is this other thing that I've recently become more enamored with, which is the idea of reliability. It's not really the same as reliability in the measurement sense. It is trying to convey, relative to the residual variance, how big is my random effect variance? And so you can compute this for intercept variance, and you can compute it for any kind of slope variance. Well, for instance, the slope variance here is the random slope variance estimate on the numerator divided by that plus this thing, which is residual variance, level 1 sample size, and the variance of the predictor that it is the slope for. So that gives it some type of effect size that you can then use to describe how much, relative to the residual variance, how big is the slope variance. So this is something that was initially, I believe, put forth by John Willett in '89 in the context of growth, and I've generalized his formula here to work for any kind of level 1 predictor. So this is another way that you might convey effect size for a random effect. But the bottom line is that random effects do not predict variance. They reallocate it. They reallocate it into new piles that predictors of fixed effects can then account for. Let's see, I think that's good. There, my goodness. I need to take a break here. Questions? Jacinta, are you dying or you have a question? Both? Yeah, she's just kind of like,
Just a quick question with the reviewing the confidence intervals. You're saying negative 0.15 to 3.59, some people are increasing, some people are decreasing, some people may not be teaching at all. When you're looking at that and you see obviously 3.59 is from 0 to another one, can you say that more people are increasing than decreasing?
Yeah, I think to the extent that the fixed slope, you're testing that against 0. So like if it were 0, then you could say that it's like 50-50. But if it's significantly greater than 0, then I think you could say that more people are increasing than decreasing. In SAS, there is a way to test individual random slopes. You would have to add the fixed slope to each person's random slope, and then you could test that against 0. So in theory, you could get an individual specific assessment. Oh my goodness. It goes from 0 to 1. 1 is biggest. Yeah, this is, so the context in which I've been working with this, let me put this back up for a second, is in power analysis. Because in order to do power analyses for longitudinal data in which you expect random slopes, at that point, none of the existing software for power analyses will spit out something, like you can't do that in G-Power or whatever. And so most of the time you end up with doing some kind of simulation. And to do a simulation, you have to have values for everything that you expect to put in your model. And it's really hard to come up with what a slope variance should be. But if you can say, well, I think I may have a slope variance with a reliability of, I don't know, like 0.5, then you can work backwards and figure out what your slope variance would have to be, and then you could put those numbers in your simulation. So that's, if you can find any previous data with which to calculate a slope reliability for, then even if your measure is not the same, because slopes are unit specific, then you could use that reliability to generate what your predicted slope variance would be for your simulation. Anyone need to do that, by the way? I saw some people go, ooh, she's going to talk about that. I have stuff. I have stuff that I've made, spreadsheets and programs and stuff. I'm happy to share it with you if you're ever in that position where you need to do power analyses. It's a whole lot of creative writing, quite frankly, but I found that this helps at least nail down something in reality that you can point to and say, well, I put this level of reliability in. So, all right. Other questions? Okay. So just a few more big picture things. It looks like we're going to end up with not having a whole lot of story time today. Surprise, surprise. Slide 43 here. So In longitudinal models, we have lots and lots of choices to make. So this is a prelude to story time. How do I approach these things? First question, what kind of model for the longitudinal aspect of the data do you need? Now, terminology that you know and the models that go with them that can help you make these decisions. On the left-hand side, on the model for the means, empty. An empty model means you don't have time in it yet. There is no change. On the right-hand side, saturated, meaning each occasion gets its own mean, meaning you've spent as many degrees of freedom as you have. Now, this one is the right answer. You're looking to compare this right answer against something simpler that gives you a trajectory through those means. That right answer is only possible when you have balanced data. So the options for what you can then do, polynomials, pieces, nonlinear slopes, this is going to depend on two things, the design and the questions. So if you have a study in which nothing happened, all you did is measure people over time, that's probably going to be described by some kind of continuous growth model. Some kind of continuous trajectory. It could be linear. If it's nonlinear, it might be quadratic, or it might be exponential, or it might be hyperbolic, or it might be something else. But it's probably continuous unless you have a reason to suspect otherwise. In contrast, if you have a study where you changed what's happening during it, like you have a baseline period, then an intervention period, and then a follow-up period, a continuous growth model likely isn't going to make a lot of sense. That's where we're into these discontinuous growth models, or what I call piecewise models, where the pieces are defined a priori based on what happened during the study, and you have to decide what shape each piece is going to take. If you have research questions about certain segments of a variable, that's another instance in which piecewise models might work. So I'm going to call on you, Amy, in your conversation we had after class. You were telling me about checking for your glucose, and how many times a day should you check? 4? 4 is good. And what happens if you check less than that? So here's time, and glucose is bad for you, right? High is bad, A1C. So if you don't check often enough, that's bad. And if you're checking more than that, yeah, because like, why do you need to check 12 times? Like, what's wrong with you? So it's kind of like, maybe, right? Yeah, but you said there was a magic range, right? What's the end of the range? 8. All right. So she wants to know if the amount of times you check over the day predicts glucose. Now, this is a study in which she didn't do anything, right? The people are just doing this on their own. But you have a hypothesis that lends itself into a piecewise account of this data. Is there a different slope before and after this magic 4 to 8 period? Is more always better? So this is an instance in which I normally would have said, well, this should just be some sort of continuous trajectory, right? But she said, nuh-uh, there's something different that happens. So to test that hypothesis, you can divide your trajectory into pieces. So that part comes from your design and your questions. On the variance side then, you have decisions to make about how these pieces or the aspects of nonlinearity vary across people. Should they be fixed, meaning everybody gets the same, or should they be random? And what do the residuals look like after you're done? That's another piece here. So this is just summarizing then what we've talked about. How do you deal with the longitudinal aspect of the data? Depends on the design, depends on the shape of the means. We can test p-values for any fixed effects. We can calculate pseudo R square for their effect on the residual variance. In building the model for the variance for time, we focus on adding to G. How many terms need random effects? Does the model fit improve? Does the -2 log likelihood go down? And then do we need to have any kind of structure in the R matrix after that? Confidence intervals and intercept-slope reliability to describe effect size. Now that's all well and good, right? So then we're at the point where we add predictors. getting time right first, then figuring out predictors and their levels of variance. And the only kind of predictors we've talked about as a class so far are time invariant. So that's what the story time review is going to start with. All right. Other questions? Okay. Do you want to end like 5 minutes early, 10 minutes early, because we're all dying? I am seriously like drenched right now. This is insane. Yeah, we can go outside and then we'll get the rain on us and we'll all catch colds and we'll be back on Wednesday, all sick. It'll be great. So I will see you then. Don't forget to do quiz 1 by 1 o'clock on Wednesday, please. And we'll have story time on Wednesday.